Hi there, I'm Axeli, and this is a little video explaining my findHopper GitHub repository. So yeah, I thought that first I would show you a little snippet of what this repository can do, like an output video, and then I will start from the beginning and explain a bit. But first, this little clip. Enjoy. So what did you just see? This was a video where on the left you could see a spectrogram recorded from a microphone over time, so a kind of a sliding window-ish video. And on the right you saw estimates of where a potential cricket might have been located. So maybe I should step back a bit. Right. Um, so for the last 2 weeks, I was lucky to be in Slovenia, and I was part of this excursion organized by Jan Bender, where we studied crickets and grasshoppers in the field. And I was part of this group with Leo and Lucy, where we had these microphone arrays. So we had these 1, 2, 3, 4 microphones, which we could place in the field. And with that, I wanted to write some code that basically can find a hopper, so find a grasshopper by using microphone audio inputs and using multiple inputs to basically do source localization. So we had these 1 meter grids in the field, and the meadow looked something like this. And from that we got these recordings where you can see the oscillograms here and some spectrograms from these 4 different microphones. And yes, so the recording I just showed you, there was this species which was probably a Pholidoptera litoralis, which was doing sounds in this range of around 10 kilohertz or so, around here, and that's what you just listened to. And basically I now want to basically walk you through the code that can create these videos. So the basic idea is that I'm using this library. Let me show you. It's called XSRP, Extensible Steered Response Power. And this is from a really nice little review. I can recommend that you have a look at it. It's really well written and kind of gives you a nice introduction to the source localization little. And to get a sense for what the output can be, let's look at some images or videos that are outputted by my code. So here we can see the structure where we have different segments over time across our 4 microphones. In this depiction you see where the source is estimated to be. So this is microphone 1, 2, 3, 4. 1, 2, 3, 4. And you see this red rectangle here quite nicely surrounded across probably what is Pholidoptera littoralis, and the reason for this red square is that when you pass in this entire signal, this algorithm would have some difficulties to estimate the source because it would have to do multi-source estimation, which is more difficult. And my solution to that problem was basically to apply masking, where we ignore this signal here and that there, because we assume that the signal comes from the same frequency band for these species. They don't vary it. And we can just look at that. And the future one could even improve this by doing segmentation on, let's say, this, that, and that, and pass those separately into the source localization algorithm. This masking was achieved by basically just applying a bandpass filter across the 6 to 9 kilohertz range. And what you also see when going here to some examples like here, you see that the position estimate is quite noisy. There's no clear point where the source could be. And this is also often related to the input data. So here we have a very noisy segment, whilst, for example, in this example, the contrast is better and the estimate is a bit better. And this is an even better example where we can clearly see the source in the raw data, and therefore also the estimate is a bit more accurate. Now this is the output images my code can create. There's also a video. I showed you it at the beginning, but I want to show you a bit more of it. So let's play this again. And have a look for basically where the different sound sources are. Particularly when it's a very confident estimate, so cases like this, here it would be unconfident, here would be confident, not so confident, not so confident, not so. More confident. This is still not perfect, but what you might have seen is that when the map here on the right, the steered response power map, the SRP map, was not had low entropy, so where the points were quite centered, and often they came from here or from here, so from the first and the third microphone, and this might suggest that there were two Pholidoptera in these two positions, and maybe they were duetting or something like that. So if you would like to use this code, I would recommend you follow these steps. So first, you clone this entire repository to some folder, and then you change your directory to that folder. So you can just write cd and then the name of this path where you save this, your terminal, and then you can follow these two steps. Write this in your terminal. This will create a Conda environment. So you'll need to have Conda installed first for this, and then if you follow these steps, it will basically install all of these libraries and their respective dependencies in that Conda environment, and then you can activate it this way. And then you can of course collect your own data and try to code with that, but maybe before then you want to test it with some sample data, the same I've been using here. So you can click on this link here, and then you can click here on download and save as and unzip this file wherever you've stored your wherever you've cloned findHopper, and then ideally you would put this in your data folder and then a subfolder, something like that. So let's talk about the code a bit. So we have different parts here. This first is you can specify a data path, so that can be a WAV file of an individual recording, or it can also be a folder where different WAV files are located, and then in that latter case it will find all the WAV files in that folder and concatenate them to one long recording. This would be useful if you use Jan's microphone array, because there are multiple WAV files, often from the same recording, because each they can only do maximum 5-minute recordings, but then if you take the folder, then it would concatenate that to, let's say, 6 5-minute recordings for a 30-minute full recording. And then here you can specify the frequency bands which you're interested in seeing the images or videos for, and doing source localization for them. And this are these bandpass filter settings for general pre-processing. This is irrespective of those frequency bands. And then this feature rate, it is used in findHopper. So findHopper is another library which is created by Iona, and that basically mimics the auditory pathway in grasshoppers or crickets. And we take the norm of in the feature space as basically a way of saying how likely at a given time point is it that there was a cricket vocalizing. And here we apply then this feed rate basically determines the temporal resolution for how many time steps we get the norm, and then in a later step you can specify a threshold which basically says, I will only segment time points where there's a peak in the norm which is above this peak threshold value, so the peak has to be at least this high, and then from that peak kind of go left and right to not the minima, but until you reach this peak boundary threshold. And then here are some further settings on how you can organize your spacing. So maybe to illustrate, let's look at one of these. And here, let me do it like that. You see these 4 grids. So in this example, we used a mic spacing of 1, which is 1 times 1 times 1 meter. And the room dimensions here specify the area around there where the algorithm searches for potential sources. So you could vary this, and you could also vary the array, or let's say you have a 4x4 array, then you would have to change some numbers here. Excuse me. And the n-grid cells is basically your resolution for the numerics of the algorithm, so it uses brute force to estimate where these points are. And you could increase this, it would take longer, but maybe the estimate would be more accurate. Then, we also have some spectrogram settings for these images here in the video. And then for the images, you can decide whether you want to create them. These ones here. And how many columns you want. So in this case, we have 3. And then you can also control whether you want to create these videos. And the FPS here basically specifies the resolution at which the, if I show you, let me close this and show this again. You see these red boxes moving here, right? And the 5 FPS is basically the resolution at which this red box moves, so you get a sense for where you are in the spectrogram based off the sound you're hearing. So the sound you hear is at a much higher temporal resolution in terms of sampling rate, but then to get a sense for that, where that is visually, I have these red boxes at currently 5 FPS. Yes. Maybe I should also go a step back. So basically, what I've been saying so far is that here I assume that you have copied the sample data from by downloading it from here, and then you have all this code and you have installed this Conda environment, and then this main point py file basically runs the code to create the images and the videos. And what I've been just talking about so far, where here's some parameters you can adjust for the plotting and your input data. So you could then, let's say if you have your own data, you could put it somewhere here in data and at the path, and then run it. And maybe I just really briefly talk about the code that I've written. So this is just some path management. This is for concatenating if you have multiple files. Here we create some folders. This is the spacing. So here you could also, if you have a different type of spacing, not a 2 by 2, so 4 microphones, but let's say 4 times 4, so 16 microphones, you could adjust that here. This is for the XSRP library. You specify how you want to basically estimate the source, and we use a really fairly simple method here, the cross correlation. In case your signal had different frequency components, so it wasn't something like a grasshopper, but something that was distinct in different frequency bands, then maybe this GCC FET method might also be helpful, but cross correlation is easier and works well for the crickets. Then this part basically just applies a bandpass filter. Then this implements Jonas findHopper pipeline to get the norm out. We use this norm to apply segmentation here. Then from that segmentation we basically find the points where in all 4 channels there's at least one segment. And then these are our seg indices, which is basically a list of start and stop tuples, where in any channel there's at least one segment found. And then this code is just basically a long way of creating the here the images, and here this creates the videos. Yeah, so I hope this was helpful. And now I think I'll still play a second video for a different frequency band, and you can just have a, if you want, listen and watch it, and maybe it's interesting. But otherwise, yeah, let me know if you have any problems with this. Then you can write a Git issue or message me per email or something like that. Best of luck with finding hoppers. So yeah, I hope you enjoyed watching that. So maybe you can have a guess what species it is. Um, Lucy thought it might be a Platycis romana, but maybe you disagree. Maybe there are different species in there. I think this recording shows nicely that it's still tricky to estimate what's exactly going on there. Are there different males? How many different males are there? What are they doing? I think better segmentation will be really helpful here. But I think this is all very promising, and I think it would be cool to use it with more data, with more microphones and that sort of stuff. And then before we close, here are still some references. This paper I mentioned, I think that's a very good start if you want to understand kind of what methods are out there for source localization. And then, of course, Jonas findHopper, I think is a great resource. And then, yeah, have a nice day. Bye.